Hello, I am Shubham Jain and I am here to present my paper, a divisionless low complexity adaptive MPPT algorithm for photovoltaic power systems. Here is a brief overview of my presentation. I'll start with introduction to solar cell operation, the variation in output power, and then I'll introduce maximum power point tracking. I'll then talk about Perturb and Observe algorithm, its adaptive variant, and their complexity. I'll then discuss the proposed algorithm with its test setup and measurement results, and then I'll be concluding my presentation. So, in this world of ever-increasing energy demand, solar energy is one of the most promising renewable energy source. A solar cell is nothing but a semiconductor device that converts light energy to electrical energy. When light is incident on the depletion region, electron-hole pairs are generated and they are drifted because of the electric field in the depletion region. This drift in the carriers generate a current that is known as photocurrent. This photocurrent, when flows through the external load, it generates a voltage that forward bias the depletion region, and because of that, forward bias current is generated in the direction opposite to that of a photocurrent. The current voltage characteristics of a solar cell is as shown. There exists an operating point at which the power of the output power of the solar cell is maximum. This operating point is known as the maximum power point of a solar cell. This maximum power point of solar cell is a nonlinear function of irradiance and operating temperature. The irradiance and temperature varies depending on the time of the day, geographical location, time of the year, and operating weather conditions. Also, the temperature and irradiance are dependent on reflection and scattering of light from surrounding. So some mechanism is required to track the maximum power point of the panel in these varying conditions. An equivalent circuit model is used for analysis of a solar cell. The equivalent circuit of a solar cell is represented in this blue box. The photocurrent IPH is the current generated due to the incident light, and this diode represents the forward bias current of the diode. RSH represents the shunt conductance, and RS represents series resistances in the solar cell. According to maximum power transfer theorem, the load seen by the solar cell must be equal to the internal resistance RS. The output power of the cell is then given as I square R equivalent, where R equivalent is the equivalent resistance seen by the solar cell. The R equivalent in terms of the input impedance of the buck converter can be given as R equivalent is nothing but the efficiency into the load of buck converter divided by the square of duty cycle. We can conclude with this that a buck converter can serve as an impedance matching device because R equivalent can be changed by changing the operating duty cycle of the buck converter. This is the basic principle of working maximum power point tracking systems. Simulated normalized power, voltage, and current results are shown in this figure, and their measured counterparts are shown in the next figure. We can see that with varying duty cycle of a buck converter, we can change the current and voltage operating point of a solar panel. The duty cycle in an MPPT system is varied according to an MPPT algorithm. Perturb and Observe algorithm, popularly known as AP&O, is the most explored algorithm in the field of maximum power point tracking. In AP&O, the duty cycle is changed by a small step in either positive or negative direction. The output power of the panel before and after the perturbation is compared. If the power is increased, the perturbation are continued in the same direction, whereas if the power has decreased, the perturbation are then continued in an opposite direction. As shown in figure, the duty cycle is changed in the same direction till the maximum power point D is reached. However, even after reaching the power point, the maximum power point, the perturbations continue with the same step size in a perturb and observe algorithm, and hence the system will oscillate around the maximum power point as shown in the figure. In maximum power point, the step size decides the dynamic as well as the steady state behavior of the system. As depicted in this graph, for a large step size depicted in red, the oscillations at steady state is larger, and for a smaller step size depicted in blue, the tracking is slow. So there always exists a trade-off between step size and oscillations. To mitigate the issues associated with the fixed step size in P&O, adaptive algorithms are reported in the literature. In adaptive algorithm, to speed up the tracking, a large step size is used in transient state, whereas in steady state, a small step size is used to avoid oscillations. In 2002, Chang and others have used a step size proportional to the derivative of output power with respect to duty cycle. Xiao in 2004 reported an adaptive algorithm proportional to the change in power, whereas AM is a constant initialized during design. Peter and others proposed a step size proportional to the derivative of power with respect to voltage in 2005. And recently, in 2020, Kim and others reported an exponentially varying step size proportional to derivative of power with respect to voltage. Now, in all of these algorithms discussed above, differentiation and divisions are common. Operations such as addition, subtraction, and multiplication can be carried out in parallel fashion. However, division is sequential in nature. So in a digital circuit, division implementation is complex. Multiple clock cycles are required for computation, which eventually increase the overall computation time. And division consumes large circuit area and resources. Therefore, algorithm involving divisions require processors of higher computational compatibility. The adaptive algorithm proposed in this work does not involve differentiation or division to calculate step size. To maintain simplicity, the step size in the proposed algorithm is kept directly proportional to the change in power. The step size is given as delta D is beta plus alpha delta P, where alpha and beta are constants with following functionality. For large change in power, alpha limits the maximum value of step size, whereas for very low change in power or at steady state, beta defines the minimum step size required. The flowchart of the proposed algorithm is as shown. The measured value of voltage and current are used to calculate power. The measured value of power is then compared with the previously stored value of power, and a new step size is calculated depending on the difference in power. This step size is either subtracted or added to the duty cycle depending on the direction of the power change. The transient and steady state parameters alpha and beta are discussed in the next slide. So in transient state, the change in power is very large. Considering the beta to be a comparatively low value, the step size is given as delta D is equals to alpha delta P. The value of alpha is chosen such that at maximum possible power change, the step size remains between 5 to 10. For step size higher than 10, the system works as expected, but large oscillations are observed during transitions. Considering maximum change of power to be 100 watt in this work, the value of alpha is calculated to be 0.05. The graph here shows the change in power with respect to time for different value of alpha and beta as a constant 0.2. The transitions in the power is due to the change in irradiance value in the simulation, we can observe that for alpha is equals to 0, the algorithm is equivalent to conventional perturb and observe algorithm. And with increasing value of alpha, the tracking time is reducing. In steady state, the change in power becomes negligible. So step size becomes approximately equal to beta. Beta ensures that step size remains non-zero even if the change in power is very small. The value of beta can be easily selected between 0.2 and 0.1 depending on the operating power level of the system. As shown in the simulation results, with increasing value of beta, the oscillations increases. So beta can be selected anywhere between 0.2 to 1. To test the proposed algorithm, a test prototype is developed. Two 50-watt solar panels with specification as shown in this table are used in series. To sense the current and voltages, resistive voltage dividers are used. Current is sensed using voltage difference across a series resistor of known value. Atmega 328 based Arduino Uno is used as ADC, data processor, PWM signal generator, as well as the display driver. An op-amp based circuit is used to level shift the microcontroller output to voltage levels suitable for the MOSFET driver. And a 12-volt battery is used as load. The buck converter in this work also serves the purpose of stepping down the panel voltage. A photograph of the test prototype is shown with annotated blocks. Here is the measurement results for the test prototype with alpha is equals to 0.05 and beta is 0.5. In starting, we can see that the step size is very large because of large change in power. The step size remains close to beta, that is 0.5 at steady states. And the variation of power due to sunlight changes due to clouds is visible here. And we can see that for these changes in power, the step size increases and again settles to 0.5. Concluding, proof of concept for a low complexity adaptive step size perturb and observe algorithm with its simulation and experimental results is presented. Working principle and design procedure for MPPT system based on proposed algorithm is discussed. Since no division or differentiation is involved, the presentation complexity of the algorithm is low. The proposed algorithm achieves better dynamic and steady state performance with computational complexity compared to conventional P&O. Due to reduced computational complexity, the algorithm can be used with any simple processor capable of performing multiplications. Here are the references for the work. Thank you very much for your time.